Okay, so last section we're going to take a look at is 3-4, and it's on what we call rational zeros, so zeros that can be represented as fractions, and synthetic division. Just so I remember, there is another name that you might see in our book called Horner's algorithm. So if you see Horner's algorithm or you see the word synthetic division, it means the same thing. Okay. I call it synthetic division. So when we are finding roots, remember we can have roots that are rational and irrational. Okay. If you solve, we had a problem kind of like this in the homework where you had to take a square root when you were done. If you solve for the roots of that problem, you're going to get x equals positive and negative square root of 3. Those are irrational zeros because the answer is the square root and I can't write it as a fraction. Now, if you solve something like, let's just say this, those have rational roots because when I factor it, even though it's quadratic, it factors nicely into x plus 1, x plus 2, and the two rational roots are -1 and -2. And those could be written as fractions. You can make anything a fraction just by putting a 1 under it. Okay. But when you have a square root involved, that's irrational. Okay. You can't write that as a fraction. Okay. Fractions have to have an integer in the top and an integer in the bottom. And that's not an integer. So we're going to look at a method we can use to figure out the rational zeros. Okay, so if there's a place where a graph is going to cross the x-axis, and you can write that as a fraction, I'm going to show you a method to be able to find it, even if it's a problem you can't factor, all right? Because maybe it's a cubic or a quartic or something higher than 2. Right? We can still find where it crosses the x-axis if it crosses at a place that's a fraction. If it doesn't cross at a place that's a fraction, then we're stuck. There's not really anything we're going to be able to do. All right, so let's take a look at this. So that's a polynomial. I'm just going to translate this. What does that say?
Is that notation?
Yeah, that's different notation. This just basically says that all the numbers in the front of the x's have to be rational. Remember, Q is the abbreviation for rational. So all the numbers, if you want to write that down, you can. All the numbers in front of the x's have to be rational. And the number in the front and the number at the end can't be 0. That's all it says. So if I ask you to apply the rational root theorem, I will give you something that fits that criteria. All the coefficients will be fractions, or capable of being written as fractions. And the first number and the last number, the leading coefficient and the constant, will never be a 0. In order to find all the rational roots, we're going to break it down into 2 steps. Rational means it's a fraction. We're going to find all the numbers that the top part of the fraction could be, and then we're going to find all the numbers that the bottom part of the fraction could be. I'm going to call all the numbers in the top part of the fraction my p-values. I'm going to call all the numbers in the bottom part of the fraction my q-values. And the way that you find all the different p-values and all the different q-values is just by looking at 2 numbers in that entire polynomial. P is always going to be a factor of the constant. So you look at the constant and you list all the factors of it. Positive and negative. So like let's say the constant was a 12. The factors of 12 are positive and negative 1, 2, 3, 4, 6, and 12. Those are all the numbers that divide into 12. So that's a lot of possibilities in this case. Q is going to be all the factors of the leading coefficient. So if the leading coefficient was an 8, the factors of 8 are positive and negative, 1, 2, 4, and 8. And then what you have to do is, once you know all the possibilities for Q, and you know all the possibilities for P, you have to write down every combination that could happen. So if the constant was a 12 and the one in front was an 8, that's a lot of different options to write out. Okay, but we just have to write it in kind of an organized, systematic way. Now, one thing to understand, this theorem generates a list of possibilities. It's not saying that every single possibility you write down is an actual answer. Okay? It only generates a list of possibilities. You then have to go through, after you generate this list, and check, do any of them actually work? So the rational root theorem just basically narrows down where it could cross the x-axis at a fraction. Then you have to go in and actually check which ones work, if any. You might generate a whole list of stuff and none of them even work. Okay, so let's try an example. So I want to list all possible rational zeros. So we're going to make a list of possibilities. So the first step is to identify the P's and the Q's. So P is any number that would be a factor of the constant. Okay. What's the constant in this case? Yeah. Negative 6. What are all the factors of negative 6? Yep.
2, 3, 1, 6.
2, 3, 1, 6. Yep, that's half of them. Yep.
Negative 2, 3, 1, and 6.
Yeah. So positive or negative 1, 2, 3, 6. Now let's identify all the Q's. Q has to be a factor of the leading coefficient. What's the leading coefficient here? Yep, 10. What are all the factors of 10?
1, 10, 2, 5.
Okay?
And then negative.
And the negatives. Positive or negative 1, 2, 5, 10. So if this polynomial is going to cross the x-axis at a fraction, which I can't even guarantee that it does, but if it does, then it has to cross at a fraction where the top number in the fraction will be one of those, and the bottom number in the fraction will be one of those. So now we have to write what those possibilities are. So let's start with picking a number for P and put that over every possible Q. So we could have a 1 in the top and a 1 in the bottom. We could have a 1 in the top and a 2 in the bottom. We could have a 1 in the top and a 5 in the bottom. A 1 in the top and a 10 in the bottom. Right, now let's go to 2. 2 in the top, 1 in the bottom. What would be my next one? Yep. Yeah, 2 over 2, but we already have that one from above, so we don't have to write 2 over 2. What would be the next one with the 2 in the top? Yep. 2 over what? Yep, positive or negative 2 over 5. And what would be the last one with 2 at the top? Yep.
It would be 1/5. We already have.
Yeah, it would be 2 over 10, which is 1/5, but we already have that one. So sometimes you get some repeats. Right, now let's do the 3 in the top. I don't think we have any that would reduce with a 3 in the top because 3 is prime. So we've got 3 over 1. We have 3 over 2. 3 over 5, 3 over 10. So those are all the options with a 3 in the top. And then how about my options with a 6 in the top? What would be, Dario, what would be the first one?
Positive or 6.
Yep, so positive or negative 6. Jaden, the next one?
Positive, negative 3.
Positive or negative 3, because it's 6 over 2, but we already have positive or negative 3, so we can skip that one. Nick, next one after that?
Positive or negative 6 over 5.
6 over 5. And Annalise, my last one? It'd be 6 over 10, but we already have that one, 3/5. So, this are all the possibilities generated from the rational root theorem. If this graph is going to cross at a place at the x-axis that can be written as a fraction, it has to be one of these values. And it might be none of them. So if it doesn't cross at a place that's a fraction, then none of these are going to work. Right? But that's how you generate the list of possibilities. So we have, what do we have? 4, 8, 9, 10, 11, 12, 24. 24 different options. What I usually do is I look for the biggest one and the smallest one. So right, the biggest one is 6, and the smallest one is negative 6. So when I set my window on my calculator, I only need to look on the x-axis between negative 6 and 6 for where it's going to cross. Okay. If all I'm looking for is fractions. So this theorem really narrows down where I have to look. Without this theorem, you'd have no idea to look between negative 6 and 6. How do you know it's not over at 27 or down at negative 80? Well, now you know that. Okay? It's got to be between negative 6 and 6. Okay. Any questions on how we got that list? Now, we're going to actually graph it, and we're going to narrow down the possibilities. Okay, so let's type it in. Okay, so we've got 10x to the 5th minus 3x squared plus x minus 6. I can do a standard window. That's negative 10 to 10. It's more than I need, but it's okay. Just make sure I typed everything in. I think I typed in everything right. 10x to the 5th minus 3x squared. Yeah, okay. All right, let's look at that. And let's start to narrow down the list. Ones that don't make sense, I'm going to cross out. Ones that could be possible, I'll circle them. Is it possible that this crosses at negative 1? No. How about positive 1? Okay, maybe. So let me just fix my symbols so you can read them. I'm going to cross out the negative 1. That one doesn't make sense. How about positive or negative 1/2? Does it look like it could cross there? No, that doesn't look. How about positive or negative 1/5? No. Positive or negative 1/10? No, doesn't look reasonable. Positive or negative 2? No, it's not near 2. Positive or negative 2/5? That's 0.4. No. How about positive or negative 3? Nope. Positive or negative 1.5? No, it's not. 1.5 is further over to the right. It doesn't look close to that. Positive or negative 0.6? Positive or negative 0.3? No, none of those look reasonable. Positive or negative 6? Definitely not. Negative 6/5. That's negative 1.2. Could it cross at negative 1.2? No. How about positive 1.2? Maybe. We gotta zoom in a little more and see. But if we were narrowing this list down to possibilities, I would say the two possibilities could be this one and that one. Those are the only two numbers in that list that would seem even reasonable. So now, what I want to do is prove that that graph only crosses the x-axis one time, and that where it crosses is irrational. So what do you think I'm going to do on the graphing calculator now to help us out? Yeah?
Second calc 0.
All right, so let's do second calc. Let's find the 0. And this one crosses at 0.9505. Why do I know that where it crosses has to be irrational? Yeah.
It can't be, it's not on our list of fractions, and it can't be made into a fraction.
Yeah, the key is that is not in the list of fractions here. 0.9505 is definitely not positive 1, and it's definitely not 1.2. Those are the only two that even seemed reasonable. And it's neither one of them. So if you have a number, and it's not in the list of possible rational options, the only other choice is that it's not rational. It must be an irrational number, right? So since the root is about 0.9505, that's not exact. So since the root is 0.9505, and this number is not in the list of rational options. That's what the rational root theorem gave us. It's not in the list of rational options. It must be irrational. Okay? Any question on that? So the goal is not to have that happen, but the goal is to actually make this list and then have one of them work. All right. So we'll do a few where they don't end up working, but then we're going to do some where they do, and that's what's really going to help us. Okay. So a lot of work with rational root theorem here, not much result. Nothing ended up helping us out. So to solve this fifth degree polynomial, it would be pretty tricky because there are no nice answers to it. So probably graphing would be the way we would do it for now. All right, so we'll come back to the rational root theorem, but we're going to combine that a lot of times with using synthetic division. The two things are going to kind of go together. So yesterday we talked about division, and we did it using long division. Okay? Long division will work all of the time, no matter what kind of problem you're trying to do. Synthetic division is a very special kind of division that works when the denominator is x minus a number. Okay? As long as you have x minus a number, this method works. If you don't, then you've got to use long division. So let's I'm going to try to do this like I did yesterday. I'll put up a problem, and we'll do division at the same time. All right. So they want me to use synthetic division here to show that this is a 0 or a root. I'm not going to directly show that that's a root. Instead, I'm going to show that something is a factor. If 3 halves is a root. What do we know would have to be a factor from what we learned yesterday? Yep.
X minus 3 halves.
Right. If 3 halves is a root, then that would mean x minus 3 halves has to be a factor. So what I'm going to show is that if I divide this by that, I get a certain remainder. What remainder am I hoping to get if that's a factor? Yep. 0, exactly. So I'm going to divide this by that, which is going to prove this is a factor. And then once I prove that's a factor, then it means that number is a root. That's how I'm going to prove it. Okay, so how are we going to do the division? Well, we could do long division, do the whole thing out and get a remainder of 0. Or we can do synthetic division. So the way we do synthetic division is we're going to put whatever you're dividing by, take what comes after the minus and put that on the outside. So it's got to be x minus a number. What comes after the minus sign, that's what goes on the outside. I think we called that number yesterday C. On the inside, you're going to write down all your coefficients. If you're missing any, you need to fill in zeros. Okay. So we've got cubed, squared, linear, constant. We're good. We got them all. So 2, -5, 1, 3. That's the setup. One nice thing about synthetic division, it's all going to fit in a very small space. Everything we do is going to fit in that box. It's not like long division where it just keeps going down to the right. They take up a lot of space. Okay, this doesn't. So we got that. And what we're going to do is bring down the first coefficient. So put a line like that. And bring down the first coefficient like this. Okay, so that's the first thing. Now, we're going to multiply the number on the outside, so the divisor, times the number we just brought down. What's 3 halves times 2? Yep. 3. And you're going to put that number right there. So multiply the divisor by the first coefficient and write the result below the second coefficient. That's what I just did. Now, big difference between this and the way we did yesterday, you're going to add the columns. You're going to add them. So -5 and 3 gives me -2. Now, you're going to keep repeating this until we're done. So let's do it again. What's 3 halves times -2? Yep. Yeah, -3. Add that column up. 1 plus -3 is -2. And one more time. 3 halves times -2. That's what we just did last time. It's -3. Add that column up. We get 0. Okay. Now we've got to interpret that last row. What do you think that last row means? It's my answer for the division problem, but I'm going to figure out what's going on there. Yep.
X squared minus 2x minus 2.
Okay, close. You're pretty close. Not quite. Anybody think, what's my quotient here? Now I guess, yeah.
Would it be 2x
2x what? Well, remember, when you divide, what do we know about the degree of your remainder compared to the dividend? What do we know about the degree of the remainder? It's always what? The same? No, it can't be the same. Yeah?
One less.
It's always smaller. It could be one less, it could be two less. It's got to be less. Okay? So the quotient has to have a smaller exponent than the original problem. So yeah, 2x squared, yep.
Minus 2x minus 2.
Right. This part is your quotient. Okay. Sometimes you've got to read it kind of right to left, so you need to see how high of an exponent you need. This is your constant, linear term, squared term. Okay. They're the coefficients that are going in front, or in that case, just the constant. What about that last number? Yeah, that's my remainder. So that part's my remainder, that part's my quotient. So what we just proved is that if you divide the original problem by x minus 3 halves, you get a remainder of 0. That means x minus 3 halves is a factor, which means the number after the 3 halves is a root. Yep. So we've proven what they wanted us to prove. So 3 halves is a root. Now, how would you have ever guessed to try 3 halves? What could have given, like I gave you this number, but if I didn't give you 3 halves, how do you think you could have gotten 3 over 2? Yep.
Dividing the coefficient by the
So I'm thinking of a theorem name. Yep.
that'd be rational root.
Yeah, the rational root theorem. That's how you would have gotten this 3 halves to begin with. You could have used rational root theorem because the factors of this are 1 and 3. The factors of that are 1 and 2. And 3 over 2 would have been one of the possibilities, and this time it would have worked. Okay. So eventually you're going to have to figure this number out on your own, and I'm not going to give you that number like I did here. But you've got the theorem to help you do that. So that's the connection between synthetic division and rational root theorem. A lot of times you use rational root theorem first, figure out the number, then you use synthetic division to divide through by that number. And the reason we would want to divide through is because every time you do division, you take this exponent and you make it smaller. If you can take your exponent and get it down to a quadratic, that's something we can always work with because we have quadratic formula. If you have a cubic and you can't get it down to a quadratic, you might be stuck. Okay? So hopefully you can find a number that when you divide, you get a remainder of 0, and you end up with a nice quadratic. All right, let's try this one. So this doesn't guarantee anything about a 0. It just says use synthetic division, ST, to find the quotient and the remainder when we do this problem. Okay. What number is going to go on the outside? Yep. Yep, so we're going to put a -3 on the outside. And what are going to be the numbers that go on the inside? Nick?
3, 7, 1, -1.
Be careful, not quite. Yep.
Maybe 3, 7, 1, 1, and negative 1. Oh, sorry, 0, 1, and negative 1.
Yeah, say one more time for me.
3, 7, 0, 1, negative 11.
There we go. So don't forget that 0 because there is no x squared term. So now that looks good, and let's go through the division. Okay, so bring down to 3. You always bring down, multiply, add. Bring down, multiply, add. That's the pattern. So bring down. We're going to multiply these together. Negative 3 times 3 gives you negative 9. And now we're going to get the next, bringing down the next number by adding that column. So 7 minus 9, negative 2. Negative 3 times negative 2, 6. Get the next number down here by adding. Negative 3 times 6, negative 18. Add that up. Negative 17. What's negative 3 times negative 17? Yep, 51. And what's 51 plus negative 11? Yeah, 40. Okay, so let's write down the quotient and the remainder. Okay, what's my quotient? Yeah.
3x squared, or cubed, minus 2x squared plus 6x minus 17.
Okay, so there's my quotient, and my remainder is 40. So what does that mean about x plus 3? Yep.
It's not a factor.
And it's not a factor of that quartic polynomial. What does that mean about negative 3? Yep.
It's not a solution.
Can you be more specific?
It's not one of the zeros.
It's not one of the zeros. It's not one of the roots. Yep. It's not one of the x-intercepts. Good. All right. So let's show that 3 is not a 0 of that. Okay. Instead of showing that 3 is not a root, what else could I show? That's equivalent. Yeah.
Could you like plug in 3 for x and see if it's a solution?
So you could plug in 3, but the problem is sometimes that arithmetic might get kind of messy if we have bigger powers. So we're going to try to avoid having to directly plug the number in. And we're going to prove it a different way. But yes. Yeah?
Show that x minus 3 isn't a factor.
Okay, let's show that that is not a factor. So all we have to do is hope we do the division and we get a remainder that's not 0. And then that'll prove that's not a factor, which proves that's not a root. So 3 on the outside, 2, 5, negative 2, negative 3. And I would argue I can probably do the synthetic division faster than someone can plug in the 3, cube it, double it, plug in the 3, square it, multiply it by 5, plug in the 3, minus the 3, and then combine all that together. I can probably do the synthetic division at least just as fast. Because I don't have to deal with powers. So, you know, this isn't even a high power, but imagine it was like to the 35th power. Well, now you're not even doing that without a calculator. Okay, but this is much easier. Okay, so bring down 2. 3 times 2 is 6. 5 and 6 is 11. Gives me 33. Add that, I get 31. Triple it, I get 93. And I'm done. So I got a remainder of 90, which means that x minus 3 is not a factor. So 3 is not a root. I don't have to deal with any powers. Much simpler arithmetic. questions on that one? So the strategies that we generally use, pretty much in that order, we always start with rational root theorem, get a list of possibilities. We're going to use the graphing calculator to narrow that list of options down. And hopefully, when we narrow it down, we find one that actually works. And then we're going to divide by the one that works with synthetic division. Dividing is always, once you factor out or divide through by that root, it's always going to take the original problem and knock the exponent down one. And that's what we want to do. Okay, we got to get the exponent down to at least a 2. Then we could use quadratic formula if we had to solve for the rest of the roots. Okay, so this is a cubic. We've got to find at least one rational root to get this cubic down to a quadratic. Okay. So right now, I don't even know what to divide by synthetically. I don't want to just start guessing. You know, should I try 2, 6, 7, 36? So who knows? So we need to generate some possible options. What would be all my values here for P? Yep.
Plus or minus 1 and 2.
Plus or minus 1, plus or minus 2. Very nice. Not a lot of options. What about my values for Q? Yep.
Plus or minus 1.
Just plus or minus 1. So this time we really don't even need Q. Q is the denominator of 1. So these basically end up being my possible rational roots. I mean, yeah, it's 1 over 1 and 2 over 1. That's just 1 and 2. So we're going to graph that. And we're going to hope that it crosses the axis near 1, -1, 2, or -2. If it doesn't, then we're stuck. We're not going to be able to do anything. But let's see if any of those look reasonable. If more than one looks reasonable, then pick one and do synthetic division. Where does it look like this graph could cross the x-axis? Yep. -1. Anywhere else? 2. So let's go to our table. And let's just check them before we actually do it. -1. Yep. 2. Yep. They both work. So -1 is going to be what we call a repeated root. So it's a repeated root because it hits it, it bounces away from it, and then it goes back up again. Let's do synthetic division with this one. And then we'll use factoring to find the other 2. So I'm going to divide through synthetically by 2. Okay. So we're going to put the number on the outside that we think is going to work. Kind of already confirmed it does using the calculator. But what I'm interested in is the quotient. I need to knock the 3 down to a quadratic. Then I can solve the quadratic and get the other answers. Okay, so let's do a 2, 1, negative, don't forget your 0. Okay. What do we know about the remainder when we divide by 2 already? Based on the calculator.
It's going to be 0.
The remainder is going to be 0. We already know we found a number that works. Okay. So bring down the 1. 2 times 1 is 2. Add that up, we get 2. 2 times 2 is 4. Add that, we get 1. And 2 times 1 is 2. Remainder is 0. Okay, so we just proved 2. Well, we technically proved x minus 2 is a factor. 2 is a root. I got 2. Now, what part of this am I interested in now? Yep.
0?
Well, I already used that fact. So I used that to prove that 2 is a root. So now we're done with looking at the remainder. Yeah,
Quotient.
we're interested in the quotient. Now, if you were trying to factor x cubed minus 3x minus 2, it factors as x minus 2 times x squared plus 2x plus 1. Well, we already set that factor equal to 0 basically and solved it. We got 2. Now set this factor equal to 0 and solve it. So we've got to factor that quadratic. How is that going to factor? X squared plus 2x plus 1. Yeah? X plus 1, x plus 1. And remember what I said about that root. I said it was going to be a repeated root because it was coming up, it was bouncing off the axis and going back down. And that's exactly what happened. What's the other root that we get that works in both of those?
-1.
-1. Yep. You don't have to write -1 twice. You just have to write it once. But it is important to understand that it's a repeated root, and you should be able to tell from the graph that it's a repeated root. Now, had you done the synthetic division with -1 first, that would have been fine. Okay? As long as you can find any number that will work from this rational root theorem and then use synthetic division, you'll get the same answers. You might just get them in a different order than I got. So I got 2 first. You would have gotten -1 first, but you still would have gotten the other answers. Okay. Any question on that one? All right, so let's find all rational zeros here. What are my p-values in this one? Yeah. Plus or minus 1. And my q values? Yep.
Plus or minus 1, 6, 2.
Yep, plus or minus 1, 6, 2, and 3. Now I've got to narrow that list down. When I write them all together, it's just 1 over all the denominators. So it's 1, 1/2, 1/3, 1/6. So really, if it's going to be a rational root, I only need to look between -1 and 1. That's a very small area to check. And now I know that's all I need to check based on the theorem. Okay, so we've got 6x cubed minus 5x squared plus 3x minus 1. I'll do zoom 6. That's a lot more than I need. So what number in that list looks reasonable based on that graph? Yeah, I would say 1/2 is the only one that's even really pretty close. So if 1/2 doesn't work, then there's not going to be any. All right, 0.5. Yeah, 0.5 is where it crosses. So 1/2 is the answer. Now, if they wanted me to then find the irrational zeros, I would have to divide through by 1/2 synthetically, and this cubic would turn into a what?
Quadratic.
Would turn into a quadratic, and then I could use quadratic formula to find the other answers. They might come out real, they might come out imaginary. Probably going to come out imaginary in this case because I don't see the graph coming back down and crossing the x-axis again. Okay. Any question on that one? So we're going to do one in a minute where we actually then take this and do the next step. which is divide through synthetically and then apply quadratic formula. Okay, so now this one's asking you to find all real. That means I want the answers you can write as a fraction and the ones you can't. Okay, so that's a cubic. Do we have a formula that we know off the top of our head to solve a cubic equation? Ethan? No, there is a cubic formula. It's very long. We don't usually teach it, at least at this level. So we need to figure out another way to solve this, which means we've got to find a rational root, then use synthetic division to turn it into a quadratic. All right. So, what are my possible p-values in this case? Yep.
Plus or minus 2.
Plus or minus, yep, 1 and 2.
Yep.
And what about my q values? Yep.
Plus or minus 3.
So if I write down all the possibilities, I have 1, 1/3, 2, 2/3. So 1, 1/3, 2, 2/3. Again, I've got a very small area to focus on now. If it's going to be rational, it's between -2 and 2. And based on the wording in the question, there has to be one, because how am I going to find the other roots if I can't turn this into a quadratic? So we've got, I need to see the question. All right, so we've got 3x cubed minus 8x squared plus x plus 2. All right, and we'll do zoom 6. And we're looking for hopefully a number in that list for a root. Okay. Which number in that list looks like it could be a root? Yep.
-1/3.
-1/3. I would say it could be. Let's go to our table and check it. -1/3. No, it's not a root. So it is a little bit off from -1/3. Okay, what's another number in that list that looks like it could be a root? Yep.
+2/3.
+2/3. Yes, +2/3 is the root. So let's divide through by 2/3 and then turn this into a quadratic. So we've got 3, -8, 1, 2. Okay, bring down my 3. 2/3 times 3 gives me 2. Add that up, I get -6. Multiply 2/3 times -6. That's going to give me -12/3. And -12/3 is -4. Add that up, I'm going to get -3. 2/3 times -3 gives me -2. Add that up, and I get 0. Okay, so we've confirmed 2/3 is a root. Yeah, you might say, well, why don't you just use second calc 0 and get these other two? This one and this one. Well, if I write down that I want the exact answer, the calculator is only going to give you a decimal. So the only way to get the exact answer is to do what we just did, and now solve that with the quadratic formula. Those are your other two answers. A, B, and C. So -b plus or minus the square root of b squared, 4ac, all divided by 2a. Becomes a plus. 4 times 3 gives me 12. Times 3 again is 36. 36 plus 36 is 72. But I can reduce that. Let's see, square root of 72 is 36 times 2. So that's 6 root 2. So 6 plus or minus 6 root 2 over 6. And everything there is divisible by 6. So final answer, 1 plus or minus root 2. Those are my other two roots. Let's see how close that was to negative 1/3. Because it looked like negative 1/3 could have been an answer. But it wasn't. 1 minus root 2. It was close. Negative 0.4, negative 1/3 is negative 0.3. So that's one of your other answers. And 1 plus the square root of 2. 1 plus square root of 2 gives you 2.414. We can confirm that's right by doing a 0. Let's see if we get 2.414. Yep, 2.414. So you probably wouldn't be able to look at that number, though, and figure out it's 1 plus the square root of 2. Right? How would you memorize all the different square roots and what their decimals could be? So you have to solve it with quadratic formula. Okay, so let's add that to our list. 1 plus or minus root 2. You only have to find those roots with the quadratic formula if they say all roots, like all rational and irrational. If it didn't ask for the irrational, then I could have stopped like I did in this problem, right there. All right. Question on that one? Okay, so yeah, we're not going to deal with that. So that's the homework. Let me just see if I need to adjust anything. Right. As I said, anywhere you see the directions in the homework that say use Horner's algorithm is just synthetic division. So we're just going to go up to, I'm going to get rid of these two, go like this. Okay. So there's no ranges of problems. They're all individual problems tonight. So page 183, all those questions. And you've got about 7 or 8 minutes, so hopefully while you're still here, I can put up the list of topics that are going to be on the test for tomorrow.